So does that make sense with the first Lewis structure? Okay. Now, the next thing I want you guys to know is after you're able to draw your Lewis structure, the next thing usually I want us to know is how to calculate the formal charge on a molecule, on each atom of a molecule. That is something I expect you guys to also know how to do, to be able to calculate the formal charge. And so I will still use this example to calculate the formal charge. And sometimes you are not able to calculate a good formal charge if you don't know how to calculate the Lewis structure, how to get to the Lewis structure. Because it is from the Lewis structure that you are able to compute the formal charge. So we'll show you an example on how to compute the formal charge here. So I will use the same Lewis structure as before, the one we had originally. And then we'll calculate the formal charge on every atom. So how do we get the formal charge of each atom there? Let's start with the central carbon. Okay, let's start with the central carbon to compute the formal charge on the central carbon. It will be a number of valence electrons. How many valence electrons do we have on carbon? Okay, carbon has 4 valence electrons. That's what we said at the beginning when we started here. You remember? We said carbon has 4 valence electrons. Okay, minus how many bonds are surrounding carbon? Guys, just give me a second, please. Let me double check one. Okay, so the formal charge for this carbon here will be the number of valence electrons on carbon minus the number of bonds surrounding carbon. So how many bonds are surrounding carbon? In this case, I will have 1, 2, 3, 4 bonds. So minus 4 bonds surrounding carbon. Minus how many lone electrons are surrounding the carbon? 0. In this case, I have 0 lone electron. So when you do that math, the formal charge on carbon will be 0. Does that make sense? Let me call this oxygen A. I will call this one oxygen B, and I will call that one oxygen C. Next thing we have to do is to calculate the formal charge on oxygen A. Okay. The valence electron, how many valence electrons do an oxygen atom have? We know oxygen, they usually have 6 valence electrons because they're in group 6. Okay. 6 valence electrons because they're in group 6. Minus how many total bonds surround that oxygen. In this case, I have 1 bond that is surrounding that oxygen A. Minus how many lone electrons are surrounding the oxygen. How many lone electrons? I have 1, 2, 3, 4, 5, 6 lone electrons. So minus 6. In this case, the formal charge on oxygen A will be minus 1. Does that make sense? Let's do the same thing with oxygen B. Oxygen B. Number of valence electrons on oxygen. Oxygen will have 6 valence electrons. How many bonds are surrounding that particular oxygen atom? We only have 1 bond surrounding that particular oxygen atom. Minus how many lone electrons are surrounding that particular oxygen atom? we have 6 lone electrons surrounding the particular oxygen atom. And these are the 6 lone electrons. 1, 2, 3, 4, 5, and 6. Okay, so minus the 6, and so that gives us a charge of -1. Then the last oxygen will be oxygen level C. Oxygen level C belongs to group 6, and that oxygen level C is surrounded by 2 bonds, and that oxygen level C has what? 4 lone electrons. So when you do the math, it gives you 0. So that's how you calculate the formal charges. Does that make sense? And one thing you need to keep in mind is that the sum of the individual formal charges equate to the total charge of the molecule, of the system. And so if we do the sum of the individual formal charges, we'll have 0 plus, or 0, let me not say 0 plus. We shall have a 0, a -1, a -1, and a 0. If you add all of these together, you will notice that it gives you -2, which is the overall charge of the system. Does that make sense, guys? Perfect. Any questions? So if you don't have any question, then I know everything is going on well for now. Now, next thing I want you guys to remember in chapter 1 is your hybridization. I want you guys to remember your hybridization in chapter 1. And in organic chemistry, we have basically 3 types of hybridization that I want you guys to study. And we'll use example number 64. We'll use question 64 as our case study. Okay, we shall use 64 as our case study. Now, the 3 types of hybridization that we know we have are the sp3, the sp2, and the sp. Those are the 3 types of hybridization that we'll need to be familiarize ourselves with in organic chemistry. Now, in the sp3, what does that mean? It means that you have 1 s orbital combining with 3 p orbital, giving you a total of 4 orbitals. Does that make sense? In the sp2, it means that we have 1 s orbital combining with 2 p orbital. So giving us a total of 3 hybridized orbitals. It gives us a total of 3 hybridized orbitals, but there is an empty p orbital hanging around. Does that make sense? There are 3 hybridized orbitals and there is an empty p orbital hanging around somewhere there. Now, in an sp, you have 1 s orbital combining with 1 p orbital. Okay, so you have a total of 2 hybridized orbitals, and you also have 2 p orbitals hanging around somewhere. That's what I want you guys to know. 2 p orbitals are hanging somewhere. Now, in terms of carbons, a carbon atom that is sp3 hybridized will be surrounded by 4 single bonds, or will be surrounded by 4 sigma bonds. In other words, okay, it will be surrounded by 4 sigma bonds. A carbon atom that is sp2 hybridized will be surrounded by 3 sigma bonds and 1 pi bond. Take note, it will be surrounded by 3 sigma bond and 1 pi bond. And a carbon atom that is sp hybridized will be surrounded by 2 sigma bond and 2 pi bonds. Usually, Triple bonds will fall in this category. Double bonds fall in this category, and single bonds will be in this category. Does that make sense? A triple bond, what you need to know is that a triple bond is made up of one sigma bond and two pi bonds. That's a triple bond. A triple bond is made up of one sigma bond and two pi bond. But if you have a molecule like ethylene, for example, let's look at this molecule here. If we have that molecule as an example, and we want to determine the hybridization of the highlighted carbon over there, okay? The first question we need to ask ourselves is, how many total bonds, how many total sigma bonds surround this carbon, the green carbon? Because the green carbon is connected by a triple bond, we know that a triple bond contains one sigma bond, okay? And then on the left side of that carbon, on this side, it also contains an extra one sigma bond. So we have a total of two sigma bonds surrounding the green carbon. Does that make sense? So we have a total of two sigma bonds. And two sigma bonds is equivalent to an sp hybridization. And the same is true with this other carbon. So as a rule of thumb, every single carbon that is connected by a triple bond is usually sp hybridized. That's a rule of thumb. Every single carbon connected by a triple bond is usually sp hybridized. Every carbon connected by a single double bond, every carbon connected by a single double bond is sp2 hybridized. Does that make sense? And carbons surrounded by four single bonds are sp3 hybridized. I will give let's do this. I usually call that a checkpoint. Let's double check this. I will give you this molecule here. Then I will highlight this carbon in the middle, okay? That's just for fun. I will highlight that carbon in the middle. Then what I will do is I will give you option A, option B, and option C. Option A, the hybridization is sp3. Option B, the hybridization is sp2. And option C, the hybridization is sp. You already know what the question will be. What is that? Usually, just give me a second. I used to do it here. I want to give you, it's like a small quiz just to test your understanding. That's what I want to do. What is it? This thing is messing me up this day. I stayed for a while without using this thing, and now I don't even know where my stuff are. What is That's not what I want. I want to give a quiz. You remember there is a way you could give a quiz so that you guys can vote and we all make a decision. Let me see this. Was it here or? I don't remember doing it here. Well, I don't think I'll be able. Oh, I think that was on Blackboard Collaborate that I was able to do it, not here. Oh, that's fine. What is the correct answer there? I wanted to share that that with you guys, but it looks like I'm not able to. So what would be the correct hybridization for the highlighted carbon in green? A, B, C, or A, B, or C? There's no way you guys can vote. I want you guys to vote. Yes, yeah, we can do that on the chat. We can do that on the chat. Okay. Yes, I've seen your responses. I've seen the responses, and I like the participation. Thank you. So let's decide. Let's decide it together and see the hybridization. Let's decide. Remember, we said everything depends on the number of sigma bonds. Okay. So let's start on the left side of the molecule. On the left side of the molecule, the carbon has a double bond, and a double bond is made up of one sigma bond and one pi bond. Does that make sense? On the right side of the molecule, the same carbon again has a double bond, and a double bond is made up of one sigma bond and one pi bond. Does that make sense? So how many total sigma bonds do we have surrounding that carbon? We have two sigma bonds surrounding that carbon. How many total pi bonds do we have surrounding that carbon? We have two pi bonds surrounding that carbon. Does that make sense? And so if we go back up here, you remember what I said up here? For the SP, you need to have two sigma and two pi. Does that make sense? So this carbon would be an SP hybridized carbon. So this particular carbon here is an SP hybridized carbon. I hope that's clear for everyone. So the correct answer here will be C. C will be our correct answer. So that said, question 64 is a good example for you guys to try your hand on, 64 is a good example for you guys to try your hand on. So over here, which indicated hybridization of carbon, oxygen, nitrogen in the following molecules. So here, this will most likely be an sp2 hybridization. This will most likely be an sp hybridization. Over here, this is most likely an sp2. This is most likely an sp3. This is most likely an sp3. This is an sp3. This is an sp. Oh, sorry. What am I saying? Here, we're indicating this bond. Because that bond originates from a carbon that is connected to a double bond, it originates from a carbon that is connected to a double bond, so that would be an sp2. This bond originates from a carbon that is connected to a triple bond, so that would be an sp. Does that make sense? That would be an sp. Over here, it would be an sp2. Okay, here same story. It is over here. It is a carbon that a carbon originates from a double bond, so this will be an sp2. Okay, on number 5, we're looking at this guy. That guy will be an sp3. Okay, and so on and so forth. The rest are sp3. So I would like you guys to be able to do that in the exam. be able to recognize the hybridization state, okay? To be able to draw those hybridization states.
I have a question.
Yes, Daniel.
So for it says in the instructions, it says indicate the hybridization of the atoms pretty much. So when you went to number 3, how did this, I don't know, I guess I'm kind of just, I don't know, would that be different if you looked at nitrogen than you would from carbon from the double bond on number 3?
No, both of them are sp2.
Okay, so both atoms would be okay.
Both atoms, yeah, because they all share that sp2 bonds. Yes, both atoms will be sp2. So are we good?
I actually had a question.
Yes.
Dang, I lost it. Never mind. When it comes back to me, I'll ask.
Okay. Then again, remember I said formal charge. Okay, you guys should know how to do the calculation. We've done an example already on how to calculate the formal charges.
Could you give me the formal charge formula one more time?
The formula for the formal charge, there are several formulas out there, but the one I like is because you only do the math. Okay, so the one I like, I would say the group number of the atom in question minus the number of bonds surrounding the atom minus the number of electrons, lone electron. Just that.
So group number minus number of bonds minus lone pair of atoms
No, not lone pair, not lone pair. Lone electron, because when you talk of a pair, you're already talking about two.
Okay.
Does that make sense?
Yes.
Lone electron, not lone pair.
Okay.
Okay, let's do an example with this one, this second molecule. Let's look for the formal charge of the carbon in the middle. That carbon in the middle there. The group number for that carbon is 4 minus how many bonds are surrounding the carbon since your mic is on?
Say it one more time.
How many bonds are surrounding that carbon?
Oh, 3 bonds.
3 bonds. How many lone electrons are there?
2.
2 lone electrons, exactly. So that's the math you have to do. And so when you do that, it gives you -1. So the formal charge of that particular carbon is -1.
Got it. Thank you.
Okay. And also, you know, when you do hybridization, you also need to remember to know the bond angles. It's important. sp3 is tetrahedral. What is that? I don't know, 104, no, 109 or 0.5 or something, 109.5. That's for the sp3. The sp2 is 120, and the sp3 is 180. Okay. It's also good to know those angles based on the hybridization. That would be a good problem there, number 72 for
Do we
you
have
guys.
to know molecular and electron, or like electron? Is that a thing? Or do we have to know both of them?
Electron domain. Usually, yes, electron domain is what is more important here because sometimes the lone pair of electron also will describe a specific angle. So I will go with the electron domain. So that's in a nutshell the kind of stuff I want you guys to remember in chapter 1. Oh, I forgot, for example, polarity. Polarity is also important in chapter 1. You know, how to determine if a bond is polar or if a bond is non-polar. And you know that if there is a huge difference in electronegativity between atoms in a bond, then that bond will be described as polar. Okay. And the sum of the individual polarity gives what we refer to as the dipole moment of a molecule. Okay, the dipole moment of a molecule. So those are the kind of things I want you guys to remember for chapter 1. Any other question for chapter 1 before we move to chapter 2? Okay, in the absence of questions for chapter 1, let me go to the end of chapter for chapter 2 and see if what we can do there. Chapter 2. This is in chapter 2. So your textbook, I like your textbook because, especially those who have this kind of copies, they usually have what they call the essential concept, things that you can quickly, go through to remember stuff. Okay, the things, some of the stuff that I want you guys to remember in chapter 2, and you have them here. Okay, now in chapter 2, first and foremost, you need to be able to determine which acid is stronger than what. Okay, how to use your pKa value, how do structures affect acidity. Those are the kind of stuff that you guys need to remember in chapter 2. It's very important in chapter 2. And also your ability to draw curve arrow. Okay, those are the kind of things I want you guys to know in chapter 2. So let's start with question number 55, for example. If I have question 55, that is asking us to rank the following alcohol from the strongest to the weakest. Okay, and with this question, we've been giving some help. We've been giving some help because the Ka values were given to us. And so based on those Ka values, we need to determine which one is what.
And
Okay?
the Ka value is equal to what?
The Ka values will tell us which acid is stronger than which one. Now, the Ka values is what we call the acid dissociation constant. Okay, and with the Ka values, the bigger the Ka value, the stronger the acid. Okay, and the smaller the Ka value, the weaker the acid. That's why you need to know with the Ka value. Now, the Ka value could be transformed to what we refer to as a pKa, which is what is commonly used. When you transform your Ka to the pKa, now it becomes the smaller the pKa value, the stronger the acid. And the bigger the pKa value, the weaker the acid. Does that make sense? Now the question is, why do we transform Ka to pKa? It's because the pKa value are easy to read because they are just natural numbers, they are just normal numbers. Like 1, 2, 3, 4, 5, 6, 7, 8, and it's easy for me to know that 1 is bigger than 0, or that 4 is bigger than 2. Does that make sense? But with the pKa value, with the Ka values, you have all this exponential. And sometimes if you are not good in manipulating figures, those exponential can throw you off. You might not know which one is bigger or which one is smaller. Does that make sense? With the exponentials, it can easily throw you off. Now,
So, a question, I'm sorry.
Yes, go ahead.
So it is a false statement to say that, if you just count the hydrogens in said acid, you'll figure out which one is the strongest.
Say that again.
Like, someone told me that if you count the hydrogens in the formula given, it's a high number of hydrogens, it would be a strong acid. Would that be incorrect?
No, I don't think that would be correct.
Okay.
Yeah. That's misleading. That would be misleading. That would be misleading. So in this case, let's look at this situation right in front of us here. Now, instead we'll be giving the Ka values. We'll be giving the Ka values, and if you look at the exponential, all the exponentials are the same. You see those exponentials? They are all the same value. 10 to the negative 13, 10 to the negative 13, 10 to the negative 13. So because those exponentials are all the same, it will be easy for you to compare their Ka value. It becomes easy to compare the Ka value. In this case, the bigger the Ka value, the stronger the acid, the smaller the Ka value, the weaker the acid. And so in this case, I know that 5.75 will be bigger than any of those numbers. And so this will be my first acid. Does that make sense? Because it has a bigger Ka value. Then this one will be my second acid, and that will be my third acid. Does that make sense? I did that comparison based on their Ka value. I did the comparison based on the Ka value. Now, let's go to question 56. Let's keep and go to question 56. Question 56 is the same type of question, asking us to rank these acids. But the problem here is that this is exponential to -5, this is exponential to the -3, exponential to the -5, exponential to the -5. You will notice that the exponentials are a little bit different. And so one thing you may want to do now is to transform this value to their pKa. Does that make sense? You transform those values to the pKa to put them on a similar basis. And so the pKa of any number is given by the negative log of the Ka. That's what the pKa is. pKa is given by negative log of the Ka value. So you might now use your calculator and then take the negative log of each of those numbers. Let me see if I have my calculator next to me so I can do that. Okay, I have it here. Let me do it. I hope I'll be able to use this. Hi, can somebody do it for me? Because I don't know how to use a calculator. Oh, God. Can someone take the negative log of those numbers for us, guys? Because I'm not very good with a calculator, so.
Okay, for the first one, I got 4.81.
Okay. Yeah, I'm really bad at using this calculator. When I was in school, we were not using this kind of complicated one.
The second one, I got 2.856.
2.86.
So we need a calculator for this test tomorrow?
Well, do you guys know what? I haven't prepared the exam questions yet. But just have a calculator.
For the third one, I got 4.52 or 4.53.
The last one, I got 4.05.
You said the last one, what is the last one?
4.05.
4.05. Now, you guys go ahead and rank them based on those pK values. Go ahead and do that. You guys rank it. Okay, now let me just give the answer. Hopefully you guys were able to rank it. So according to this, the smaller the pKa, the stronger the acid. So this is my strongest acid here, number 1. My number 2 my number 3, and my number 4. That's the way I will rank them. Okay. So here we've just seen how we can use the Ka value to rank the acid, and we've seen how we can use the pK value to rank them. Okay. Now let's go back to 55. 55b says I will need to explain the relative acidity. To explain the relative acidity. Remember, we've ranked them as 1, 3, and 2. So we need to explain why is that so. Okay. And in order to explain relative acidity here, there are some factors that you guys need to consider. There are some factors you guys need to consider. First thing you need to consider is the electronegativity. How does electronegativity affect acidity? Okay. How does it affect acidity? A hydrogen atom that is connected to an electronegative atom is acidic. Does that make sense? Those are the factors that affect acidity. Meaning that if I have meaning that if I have, for example, an NH versus an OH, okay, I want to compare these two here. Which of this hydrogen is more acidic? The first question you need to ask yourself, between nitrogen and oxygen, which one is more electronegative? I guess oxygen is more electronegative. And so the hydrogen atom connected to the most electronegative atom is the more acidic. So in this case, this will be my most acidic. And this is only true, take note, this is only true when you are comparing atoms of the same period. When they're in the same period of the periodic table. That's where electronegativity is important. Does that make sense? Now, second thing you need to take note when you're doing a comparison, sometimes we'll refer to that as the size. This is good, the size. The size here becomes important when you are comparing atoms in the same group. When you're comparing atoms in the same group. For example, if I have HF versus HBr, I'm comparing them. You have to look at their sizes now. Fluorine is smaller in size compared to bromine. And so because bromine is bigger in size, this will be the stronger acid. In other words, some people will look at it from the conjugate base point of view. You will say that bromine being bigger in size will form a more stable conjugate base. That's why HBr is a stronger acid. Does that make sense? Bromine is bigger in size, and so will form a more stable conjugate base and making HBr a better acid, a stronger acid. That's the way I want you guys to look at it. Now, other factors that we'll be looking at, we might see it in the future, will be hybridization. Another factor is hybridization. You may use hybridization to explain the acidity. For example, in hybridization, if I have a hydrogen connected to an sp3 carbon, and I'm comparing it to a hydrogen connected to an sp2 carbon, and I'm comparing it to a hydrogen connected to an sp carbon, which one is more acidic? The more acidic one will be the hydrogen connected to an sp carbon. So in terms of hybridization, hydrogens connected to an sp carbons are more acidic than the one connected to an sp2 carbon, which in turn are more acidic than the one connected to an sp3 carbon. That's how hybridization will affect acidity. Does that make sense?
Does this go with any other atom per se?
Yes, for any atom, even the hydrogen or even an oxygen, it will work that way.
Can you repeat it again?
So in terms of hybridization, a hydrogen connected to an sp carbon is more acidic than that connected to an sp2, which is more acidic than that connected to an sp3. So that's how hybridization affects. And so usually when we ask you guys to explain the relative acidity, we want you to use one of those factors to explain. So you have to know which factor best explain what I'm observing, and then use that factor to explain. The fourth factor is what we call distance. Distance is also an important factor in this case. And usually distance can match up with electronegativity or with any of these. Distance per se is not a factor on its own, but you can use distance with all of these three factors here. And in terms of distance, what I mean is, where is the hydrogen located with respect to those three factors that I said above? Okay. If the hydrogen is very close to an electronegative atom, the effect will be bigger. But if the hydrogen is far away from the electronegative atom, what happens? The effect will diminish. Does that make sense? That is true with hybridization also. And usually that works through what we call the inductive effect. So we refer to that as the inductive effect. The inductive effect will die down with distance. As you go further, induction decreases. Does that make sense? So if we go to question 55, if we compare this oxygen here, the hydrogen, because this is the most acidic hydrogen. The most acidic hydrogen is the one connected to, our most acidic hydrogen is the one connected to the oxygen, because the oxygen is the most electronegative atom. Then you have a chlorine here. In terms of electronegativity, you have 2 chlorine atoms versus 1 chlorine atom versus 3 chlorine atoms. So because you have 3 chlorine atoms, so this gives you a stronger electronegative pole. Does that make sense? This 3 chlorine atom gives you a stronger electronegative pole, meaning a stronger inductive effect, and by so doing, rendering this hydrogen more acidic. That's why this hydrogen was also ranked number 1. Does that make sense? The other hydrogen that was ranked number 2 is because it is connected to a molecule with 2 chlorine atoms. So this 2 chlorine atom will definitely exert a stronger electronegative effect compared to 1 chlorine. Does that make sense? And so the guy with the 2 chlorine will have a stronger inductive effect compared to the one with only 1 chlorine atom. So that's why this was our number 2 and this was ranked number 3. So that's the way you will be able to explain those kind of stuff. Now, in 56, 56b says, how does the presence of electronegative substituents such as chlorine affect acidity? How does the presence of that electronegative substituent? This is our acidic hydrogen here. That's the acidic hydrogen. This is where distance becomes important. How far is the chlorine from the acidic hydrogen? And the first thing you need to know is, when we're looking at those distance, you want to count maybe the number of carbon atoms that are away from, from each other. That's where the distance comes in, number of carbon atoms. So let's start with the first molecule here, this guy here. We don't have any chlorine atom on that molecule. Do you see that? And so because we don't have any chlorine atom, we classify this as the least acidic. So we keep that aside. It was classified as the least acidic. Now, when we move to the next molecule, the oxygen and the chlorine are separated by 1 carbon. in terms of distance. When we move to the other one, the other molecule here, we notice that the hydrogen is separated from the chlorine by 1, 2, 3 carbons. Do you see that? Because the chlorine is attached on the 4th carbon. And the next one, the hydrogen is separated from the chlorine by 1, 2 carbons. So this is the effect of distance here. You notice that this is the strongest because the chlorine is closer to the hydrogen. So the inductive effect is stronger. Followed by this one, because it's only separated by 2 carbons, whereas here the separation is 3 carbons. Do you see that? So that's how electronegativity is important, the distance. The further the distance, the weaker the inductive effect and the weaker the acidity of the hydrogen. The closer the distance, the stronger the inductive effect and the stronger the acidity of the hydrogen. That's what I want you guys to know. Does that make sense? Then the last factor that we haven't talked about is resonance, which I would say number 5. Factor number 5 is resonance. With this one, all you need to know is that the more resonance structure you have, the stronger your acidity. Does that make sense? The more resonance structure, the stronger the acidity. Any questions, guys? Any question?
Is this all that we're going to is this all that we're going to need to know for the exam, or we're going to have to?
For chapter 2, we've done with chapter 1 already. Remember, the exam is chapter 1, 2, 3, 4.
Oh, okay. I was making sure.
Yes. So I'm just giving you a highlight of the kind of stuff that I expect you guys to know, have a good understanding to be confident when you're taking your exam. Any other questions, guys? You know, I may not be able to cover like everything. I'm just giving you, quick overview of the kind of stuff I expect you guys to know.
For resonance, how do you know how many resonance a molecule has just looking at it, by looking at it?
Just by looking at the molecule?
Yeah.
Okay. Let me see if I have a question that will require us to use resonance. Let me see. I'm just quickly glancing through this to see if there's any question that require resonance to answer.
Is our exam timed?
Yes, it will be time, an hour and a half.
Okay, and is multiple choice or is it different?
It will be multiple choice, but there will be some questions that will require you guys to also draw structures. But there will be no reading passage. It will be either multiple choice or you'll be required to draw a molecule.
Okay, yay.
Are we allowed to use scratch paper?
Yes, you're allowed to use scratch paper.
Okay, because I just want to make sure, because you know that you are,
I'll be watching you guys, right?
you know, I don't want to make it seem like we are cheating, but just, you know, just scratch paper.
Yeah. Yes, you will be allowed to use scratch paper. So, yeah.
Will the recording be available after this?
Yes, I'll make it available either on Blackboard or on the YouTube, then share the link on Blackboard.
Okay, thank you.
Yeah. So let's go to chapter 3. Let's go to chapter 3. Chapter 3 is mostly nomenclature, isomerism, and stuff like that. That you guys need to know. All those confirmations, staggered confirmation, and all those kind of stuff. Now, first and foremost, in terms of nomenclature, I may not ask you probably to name something or draw the structure or something, but because most of the questions, sometimes if you don't know the names or if you don't know how to draw a structure, it might be difficult for you to answer the question. So that's probably the way I'll be testing you. Okay, by just giving a name and then asking a problem. So you guys will have to be able to know what the structure is in order to answer that problem. So sometimes that's how the nomenclature will go. Now, being able to determine between cis and trans isomers of cyclohexane is very important. That's something I will test you guys on definitely. How do you know if an isomer is cis? How do you know if an isomer is trans? How do you know which of the cyclohexane is more stable than the other one? Those are the things I want us to look at. So I will use question 58 as a sample to quickly go through the kind of stuff I want you to know on cyclohexane. Now, on cyclohexane, I want you to be able to determine cis versus trans. Okay? On a cyclohexane, there are two types of bond. Basically, on every cyclohexane, you always have the axial bonds and you have the equatorial bonds. So let me draw a hypothetical cyclohexane molecule here. This is a hypothetical cyclohexane. In this cyclohexane, there are 12 bonds. Some of the bonds are pointing straight up or straight down, straight up or straight down. How do I know which bond will be pointing up and which one is pointing down? If you notice, you'll see that the junction here between this carbon bond and that carbon bond is kind of already orienting itself in the up direction. Because it's orienting itself in the up direction, that's how I know that this bond will be pointing up. If you look at this connection here, this bond connecting to this one, you see it is already pointing towards a downward direction. That's how I know the bond will be pointing down. Does that make sense? If you look at this connection here, and you look at this connection here, if I want to draw a bond at this point, how would the point be? How would the bond be? Pointing up or down? I guess most of you have it correct. That bond will be pointing up. Because you see those two bonds are already in the pre-up direction. You know, I don't know if that's correct, but that's basically what I want to say. So it's the same story with this one, and it's the same story with that one. Now, all these bonds that I have drawn are referred to as the axial bonds. Does that make sense? Those bonds are referred to as the axial bond. Now, there are another series of bonds that are pointing away from the ring. So away from the ring, it means this will be pointing in that direction. Away from the ring, it means it will be pointing in this direction. Away from the ring, you are pointing in that direction. Away from the ring, you are pointing in that direction. Down here, away from the majority of the ring, you'll be pointing in this other direction. Oh, sorry, I forgot to draw another axial bond here. I forgot there's another axial bond here. And then there will be another equatorial bond that is pointing away from the ring. Now, the bonds that are shown in red are referred to as equatorial. Does that make sense? The bonds shown in red are referred to as equatorial. The bonds in blue are represented as axial bonds. Now, for every particular carbon atom, let's take this carbon atom here, the one highlighted in green. For every particular carbon atom, there are two types of bond. There is one axial and one equatorial, right? But then, what are their relative position? What are their relative position? What I mean by this is this. On this carbon atom, the blue bond is pointing upward relative to the red bond that is pointing downward. Does that make sense? If I go to the next carbon atom, this one here, the red bond is pointing in the upper direction relative to the blue bond that is pointing in the downward direction. Is that okay? If I move to the next carbon here, the blue is pointing in the up and the red is pointing down. If I go to this one, the blue is down and the red is up. If I go to the next one, the blue is up, the red is down. If I go, Anik, yeah. If I go to the next one, which is this one here, the red is up and the blue is down. Does that make sense? So that's what we refer to as up bonds and down bonds. You need to be able to do that. You need to be able to do that. Once you've done that, now we can do everything. Now we can go ahead and play. Now we can now derive our rules, okay? Up, up, or down, down equals cis. Does that make sense? Up, up, or down, down equals cis. Up, down, or down, up equals trans. Is that okay, guys? Meaning that if the substituents are on the up-up bonds or both substituents are on the down-down bonds, then you have a cis. If both substituents, one of them is up, the other one is down, then you have a trans. Does that make sense? So that said, let's answer A. Is A cis or trans? Here, I have a methyl group pointing in this methyl group is there. Then it means that I also have a bond here, okay? And that bond will probably have a hydrogen. On this other one, this is a methyl group here. Then I will have the bond here, which will have a hydrogen. I am doing that based on this template. You see the template that I have, based on my template. Now, based on that template, guys, you notice that this methyl group here is up with respect to the hydrogen. So the methyl group is up with respect to the hydrogen. On this other one here, the methyl group is down with respect to that hydrogen. Does that make sense? So this is an up-down situation. An up-down situation is a trans. Does that make sense? An up-down situation is a trans. So let's go to structure B. In structure B, I will have a bond here and I will have a bond here. This will have a hydrogen, this will have a hydrogen. So in structure B, this is down and this is up. So in this case, I also have a trans. Does that make sense? On C, I have a bond here with a hydrogen and then I have a bond here with a hydrogen. So in that case, this will be down and this will be down. Does that make sense? So they are both down, down. So this is a cis. Then the last one, I have a bond here and I have a bond here. This is an up and that's an up. So this is an up-up situation. So that gives me another cis. Any questions, guys?
Could you do one more example of the cis and trans?
Of another example of the cis and trans?
Yes, can you do another example of what we just went over with trans and cis and determining which is which?
Okay. Let's do 68. 68 B and C, okay? Let's do 68 B and C. But this one is asking us for which one has the highest energy. Let's forget about that. Let's give them the cis and trans. Let's find out which one is cis, which one is trans, okay? For this one. Now, 68. Here I will have a bond pointing here and I will have a bond pointing here. The methyl group is pointing up with respect to this hydrogen, and the chlorine is pointing down with respect to that hydrogen. So this is an up-down situation. Up-down is trans, okay? Molecule B, I have a bond here and I have a bond here. For the first case, the methyl group is pointing down with respect to that hydrogen, and the chlorine is also pointing down with respect to that hydrogen. So this is a down-down situation. So this is a cis. Okay. Molecule C, the methyl group is pointing up with respect to that hydrogen. And over here, the chlorine is pointing down with respect to the other hydrogen. So this is an up-down situation. So that will be a trans. Does that make sense?
Yes.
Okay.
I had a quick question relating to the cis and trans as well. So is it possible for you to give us like all the variations of cis and trans? Like I see trans is up, down, cis is down, down. Are those just the two variations that there will always be, or are there more?
Those are the only two variations, depending once these are the only two variations here. You see this?
Okay.
Up or down, down gives you cis. Up, down, or down, up gives you trans. Does that make sense? The key to this thing is to be able to have this, you know, to be able to know which bond is up, which bond is down. That's what is key. Does that make sense?
Yes. Could you scroll back up for just a hot second?
Say that again.
Could you scroll back up to where it says the up, up, and the down, down? Thank you. That's good. That's all I needed.
Okay. Now, the next thing I want us to do now is stability. The next thing I want us to do is stability. We have the axial and the equatorial, right? Now, in terms of stability, when your substituents are on the equatorial bond, the molecule is more stable compared to when the substituents are on the axial bond. I repeat, when the substituents are on the equatorial bond, your molecule is more stable compared to when the substituents are on the axial bond. Is that okay? So here we need to find out, remember all my equatorial bonds are the red bonds. So if your substituents are on the red bonds, you will have a more stable molecule compared to one in which the substituents are on the blue bonds. Okay? That said, I want us to do a comparison in terms of stability now of molecule A, B, C, and D. Okay? Let's do a comparison of stability. Now, let's start with molecule A. Okay? Molecule A, this methyl group is on the axial position. So I will write that as A. And this other methyl group is on the axial position. On molecule B, this methyl group is equatorial. You can see it's on the red bond. And this one also is on the red bond, it's equatorial. C, this guy is equatorial and this guy is axial. D, this guy is axial and this guy is equatorial. Now, if I ask you to rank this molecule in terms of stability, which one is the most stable? The most stable is the one in which the substituents are in the equatorial position. And in this case, B will be my most stable molecule. because both substituents are equatorial. That's why B is the most stable. The least stable molecule will be A. A will be the least stable molecule because both substituents are axial to each other. That's why it will be the least stable. Now, the stability of C and D would be the same. C and D will have the same stability because the substituent, one is on the axial, one is on the equatorial, so the stability will be the same. Does that make sense, guys? If that is clear, let's go back to this one, 68. So if that is clear on 68, I will want you guys to rank this in terms of their stability. We have A, B, C. Which one is which? Now, in A, this is on the axial, this is on the axial. Do you see that? In D, this is axial, this is axial. And in C, all of them are axial. Well, this will not be a good example. This is axial and this is axial. They are all axial. So this has to do with distance. This doesn't explain the concept I want us to look at. Let's see. Well, I don't have a typical example of the concept I want us to look at, but what I want you to remember is that once the substituents are on the equatorial position, they are more stable compared to when they are on the axial position. That's the first thing. Now, second thing with stability, if all the substituents now are on the axial, just like in number 68, in order to determine stability, you have to make use of distance. You have to make use of distance. In C, the groups are far from each other compared to the other one. So distance now becomes important. Is that okay? So my 1, 4, this one will be more stable, followed by this, and then that one. Are we good with cyclohexane? Those are the kind of stuff I want you guys to know with cyclohexane. Any questions on cyclohexane?
I have a question.
Yes.
So if you're doing the axial and equatorial, right? And
Yes.
you're naming it. So how about with putting it in the correct order if you have two that has axial and then the other two is axial, equatorial, and then one that has like equatorial, equatorial? Like how would you put that in order?
Well,
if two of them are the same.
You might want to look at their distances, okay? The ones in which the substituent, there might be two axial, there might be two equatorial, or two axial, but if their distances are not the same, you want to take the ones that are further apart from each other. Does that make sense?
Yeah, that makes sense.
Yeah. The distance also is important. Remember, I will not be able to go through everything. I'm just giving you some, important points. I'm just giving you some really important points. So I will also quickly go through chapter 4. Let's quickly look at chapter 4 also. Chapter 4 has to do with your stereochemistry. So in chapter 4, for example, let's look at question number 68. 68 says, name the following compound using the R and S designation. Okay. I will not necessarily name the compound, but the most important for me is how do you determine if a molecule is R or if a molecule is S? Okay, that's basically what is important for me here. Okay, how to know if you have an S or an R molecule. Now, 68A is an example of what we call a Fisher projection. Okay, we refer to that as a Fisher projection. And in the Fisher projection, basically, okay, what you have on the Fisher projection is that all the bonds that are horizontal, are vertical, are pointing backward. All the vertical bonds are pointing backward. That's what you need to know. And all the horizontal bonds are pointing forward. That's a template for the Fisher projection. Okay, so if I look at 61A, it means that this group is pointing back, this group is pointing back, and then these groups here are pointing towards you. That's what you need to remember in the Fisher projection. Okay, now, to determine the R and S configuration, you need to be able to do what we call the priority ranking. You need to rank the group that surrounds a chiral carbon in terms of priority, and that priority depends on the atomic mass of the atoms surrounding the carbon. So, if we take the first example, oops, it's taking time to load. Yeah. If we look at the first example, this is my chiral carbon here, okay? And I'm looking at all the groups surrounding. I need to give them priority. The highest priority will be given to this oxygen here. So that's my priority number 1, okay? And in terms of atomic mass, because oxygen is heavier than hydrogen, heavier than carbon, heavier than carbon, okay? The second priority will be given to this carbon here. That will be my carbon number 2. Because this carbon here is connected to a chlorine, whereas this other carbon is connected to a hydrogen. So that will be my second priority. And so this one will be the third priority. Now, when I'm able to rank my first, second, third priority, I now draw an arrow in that direction. And so my arrow will lead from the first to the second to the third priority. That will be my direction of the arrow. And now ask yourself, is this arrow in the clockwise or the counterclockwise direction? Let me see. Sometimes I don't know, right? So this is counterclockwise. Okay, this arrow is traveling in the counterclockwise direction. Now, because the arrow is traveling in the counterclockwise direction, this will be referred to an S. Does that make sense? This will be an S configuration. But take note what I said at the beginning. At the beginning, I told you guys that every substituent on the vertical bond are pointing away from you, whereas substituent on horizontal bond are pointing towards you. And in the rule of determined stereochemistry, the lowest priority must always be pointing away from you, meaning on the dash bond. The lowest priority must always be on the dash bond. And in this case, our lowest priority is hydrogen. And according to the Fisher projection, this hydrogen is pointing towards you and not away from you. And because the hydrogen is not pointing where it's supposed to be, we shall now reverse this configuration. Instead of calling it an S, we'll refer to this as an R. So that will be the R configuration. I will take again the other one. This is another chiral center here. Let's do a second example. That's another chiral center. The first thing we need to do is to give them priority numbers. That's the first thing we need to do. Give them priority number. In this case, this will be priority number 1. This will be priority number 2. And this is priority number 3. So I'll be traveling in this direction. Which direction is that? That is a counterclockwise direction. So I'll be tempted to call this an S. But then my lowest priority, which is that hydrogen, is pointing towards me. Because it is pointing towards me and not away from me, I will reverse that configuration, and this will now be an R. So this molecule here is an RR molecule. Does that make sense? This molecule is an RR molecule. Let's go to part B. B, this is my chiral center. This is my priority number 1. This is my priority number 2. And this will be priority number 3 here. Okay? And so I'm traveling in this direction, 1, 2, 3. That is the clockwise direction. And the clockwise direction is an R. But then this is my priority number 4. Is my priority number 4 away or towards me? According to my Fisher, it is towards me, which is bad, because the priority number 4 must always be away from me. And so because he's pointing towards me, this guy will reverse and he becomes an S. Is that okay? That will reverse and becomes an S. C. Let's look at C. Let's consider this chiral carbon here. Give them priority numbers. This is priority number 1. This will be priority number 2, and that will be priority number 3. This is priority number 2 because that carbon is connected to a bromine, whereas this is priority number 3 because it's connected to another carbon. And so I'll be traveling in this direction, 1, 2, 3, which is the counterclockwise direction. Counterclockwise means S. Now, my priority number 4 is this guy, the hydrogen. Question, is that hydrogen pointing towards me or away from me? In this case, the hydrogen is pointing away from me because it's on the dash. So the hydrogen is pointing in the right direction where it's supposed to be. So I will maintain, this will be maintained as S. Is that okay? That will be maintained as S. This is another chiral center here. This is my priority number 1. This is my priority number 2, and that will be priority number 3. So in this case, I'm traveling in this direction. That is a clockwise direction. That's a clockwise direction. Clockwise means R. Oh, guys, yeah, that's clockwise, right? Yeah, that's the clockwise direction. It means R. Now, which one is the lowest priority? The lowest priority is this group. Is the lowest priority on the dash or the wedge? Meaning, is it pointing away from me or towards me? In this case, it is pointing towards me, which is bad. I always want the lowest priority to point away from me. So because it's pointing towards me, I have to reverse that configuration and it becomes an S. Does that make sense? That's how you have to determine the absolute configuration, the R and S. So that's one thing I expect you guys to be able to do. That's one thing I expect you guys to be able to do. Let me see.
Do we not have to know Newman projections?
Yeah, you will need to know those Newman projections. You will need to know those Newman projections. That's important. Know the staggered, the eclipse, and the gauge conformation. You know, and you also need to be able to distinguish between enantiomers, between diastereomers, and stuff like that. I expect you guys to be able to do that.
Can we go over those diastereomers?
Okay, yeah, we'll go over those. We'll go over those. Let me look for one question that will help us do that. Let's look at question 79. Question 79 says, are the following pairs identical? Enantiomers, diastereomers, or constitutional isomers? That's question number 79. Now, I always have my little cheat sheet with me. When you have a molecule with two chiral centers, okay? When you have a molecule that has two chiral centers, these are the different possibilities. Both centers could be RR, or both centers could be SS, right? One center could be R and the other center would be S. Or one center could be S, then the other center will be R. Now, how are these molecules related? If the centers are exact opposite of each other, that relationship is known as enantiomers. So I will call it E, okay? If the centers are exact opposite of each other, then we'll refer to them as enantiomers. So here, they are exact opposite of each other. So these are enantiomers. Does that make sense? Now, if one center is RR and the other one is RS, then we'll refer to them as diastereomers. If one center is SS and one is SR, then it will be referred to as a diastereomer. And the same is true with this one. This will also be a diastereomer.
So it's between two different molecules, not like within the same one.
No,
right?
it's between, it's between isomers. I'll put it that way. Between isomers. We'll do some examples here, you will see. Here also, you will have a diastereomer relationship. Let's do an example. Let's look at A. Let's do 79A, okay? Let's do 79A. 79A, let's look at this chiral center here, and then we'll also look at that chiral center. Let's start with the first chiral center here. Okay, now, with this chiral center, you'll notice that there is a bond that hasn't been shown, and that bond would be the broken bond that contains a hydrogen atom. Okay, it will be the broken bond with the hydrogen atom. Now, which one is priority one? This is my priority number one. Okay, and this will be my priority number two, and this will be my priority number three. Is that okay? The one that is priority number two is because I have a carbon connected to two other carbons. And then priority number three is a carbon connected to only one other carbon. Okay, that's how I give my priority. So my direction will be this way. That is a clockwise direction. Do you see that? That's a clockwise direction. And I will maintain that clockwise direction because the hydrogen is on the back. So clockwise, it means it's an R. Does that make sense? Let's do the same thing with the second one, the second chiral center. Let's look at this chiral center here. Let's look at this chiral center here. This is, which one is one? This is one. And then this will be two, and this will be three. So I will travel in this direction here. 1, 2, 3. Which direction is that? Is that a clockwise or counterclockwise? Counterclockwise. S. The hydrogen is on a broken bond, which hasn't been shown. And that hydrogen is at the back, which is fine. So this is an RS structure. Does that make sense, guys? This is an RS structure. Let's go to the other one here. With this other one, the first center here, this first center, you notice that it's exactly the same as this other center. Do you see that? The molecules are placed exactly the same. So I won't waste time. I will refer to this as an R. Is that okay? If you look at the second center here, you see that this second center is the opposite of the other one because the CH3 now is on the dash. So the configuration will also be the opposite. So this will be an R configuration. So this is how you save time. You don't want to go and keep repeating the same stuff that you've done already. Is that okay? Now let's compare and find out the relationship. Are these identical? Are they enantiomers? Are they diisomer, or are they constitutional? Now, when I look at this, I have an RS and an RR. According to this chart, what does that give us? When you have an RR and an RS, what relationship is that? So those are diastereomers. Does that make sense? So these A are diastereomers. Now let's look at B. Let's look at B. B, this center will be R and this center will be S because it's exactly the same as this one here. Over here, this will be the reverse, okay? So this will be S and this will be the reverse. So this will be R. So in this case, you have a relationship RS and SR, which is what? Opposite of each other. You have RS and SR. What relationship is that? Enantiomer. Do you see that? Those are enantiomers. Let's go to structure C. Structure C, this is R, this is S. And if that's R, that is S, then let's see. It's taking some time to adjust. So RS, so this is the reverse, so this will be S. And then up. Be careful, guys. Be careful. C is a little bit tricky. We need to be careful. We need to be careful. Do you see why we need to be careful with C? Because they decided to switch the CH3 and the chlorine. Do you see that? The CH3 and the chlorine were switched. So we have to do the calculation again. We have to go back and determine the absolute configuration. We have to do that in this case. So we need to be careful. So in this case, this will be carbon 1, that will be carbon 2, and that's carbon 3. So I will travel in that direction, which is a counterclockwise direction. Then I will reverse it. This become an R. I reverse it because the hydrogen, the bond that hasn't been shown is the OH bond, and the hydrogen will be connected on that OH bond. Then the other one, which is this one, this is my 1, this is my 2, and that's my 3. So I'm traveling in that direction. So which is the counterclockwise direction? Is that? No. Guys, help me. Sometimes I'm confused. The green, the red direction, this one here, which direction is that? Is that clockwise or counterclockwise?
The red one is clockwise.
So clockwise, so we need to reverse it.
And the blue one is counterclockwise.
Okay, so we'll reverse this clockwise, so this becomes S, and this will reverse it, it becomes R. Does that make sense? Now, what is the relationship between this molecule? In C, can someone tell me? What's the relationship here? Be very careful before you give me an answer. What's the relationship in C?
Is it E?
No. It's not E.
Oh, they're identical?
Mm-hmm.
Huh?
Bingo. They're identical. Bingo. Look at this, guys. The center with the chlorine atom is R. And down here, the center with the chlorine atom is also R. Then, the center with the methyl group is S, and the center with the methyl group is S. So it's the same molecule. Do you see that? This is the same molecule. It's different from B. In B, the center with the chlorine is R, and here the center with the chlorine is S. So they are opposite. The center with the methyl group is S, the center with the methyl group is R. So they are opposite. So these are exact opposites of each other. This is why E is enantiomer, but C will be identical. Does that make sense?
So we should be comparing like each group, like trying not
Each
to look at
center, yes, each center. That's what I mean. That's what I mean by exact opposite. Not just opposite, but exact. Does that make sense? So with D will be constitutional isomer, because you notice that there is one carbon separating the chlorine from the metal in one structure, whereas the other structure, there is no carbon separating them. So these are constitutional isomers. You don't even need to worry about determining the absolute configuration.
Constitutional is when it's like different
Connectivity, yes, different connectivity. So in D, those molecules are connected differently, so they are constitutional. Does that make sense, guys?
Yeah, that makes sense. I have a question on how you number it in order to know if it goes clockwise or counterclockwise.
You give them priority. The heaviest atom or the heaviest atom has priority number 1, and so on and so forth. Does that make sense? You give them numbers.
Okay.
Yeah. So let's do that again for this one here. Let's do that again for this one here. Oh, yeah. So for this one, I will call this is my Cara center. So I will call this one 1, then I will call this one 2, and I will call this one 3. Let me explain. 1 is 1 because chlorine is heavier than this carbon or this other carbon. So that's 1. Now this one, I call it 2 because this carbon is connected to 2 other carbons, whereas this carbon is only connected to 1 other carbon. So that's why I call this 2 and the other one 3. Then you can now give the direction. Okay. So that said, I will say good luck. You guys should go and then finish up with your quiz. If there is no other question, then I'll probably call it a day and say
I
good
had a
luck.
quick question about the naming. We don't need to know anything about naming them. As far as like counting the carbon structures, like what the homework was over, we don't need to know that.
I think he muted himself.
I see that. I guess he said he's done.